Module 2, Lecture A, Numbers and Bool. By the end of this lecture, you will be able to use int, float, complex, and bool to construct scalar values from various input types safely. Predict how Python 3.12 evaluates truthiness and numeric conversions in common expressions. And apply sum, min, and max to numeric iterables while handling edge cases such as empty inputs. Building numeric values. Parsing integers safely. Safe integer parsing means turning unpredictable text input into a trustworthy whole number while handling problems carefully. In practice, data from web forms or configuration files usually arrives as text, and Python can convert this text to an integer only when it is in a valid numeric format. If the text is malformed or represents a number that is too large, a direct conversion can fail and cause errors. To avoid this, you should anticipate invalid inputs, validate them, and handle conversion failures gracefully, instead of assuming every string will convert correctly. When parsing integers in Python, it is important to know which inputs are actually valid numbers. Even strings that look like simple values, such as ages or counts, may contain spaces or symbols that make them invalid. Values with decimals or scientific notation must be cleaned or converted before they can be treated as integers. In real data pipelines, you may also see empty strings or placeholders like none or NA that cannot be parsed. You need to detect these patterns and decide whether to use a default value, skip the record, or raise an error to keep your data consistent and reliable. When parsing integers safely, you need to consider the numeric base, the sign, and the allowed range. Python can read numbers in bases other than 10, such as binary or hexadecimal, but you must specify the base to avoid mistakes. Decide whether negative values make sense for your situation and enforce that rule after parsing. Also, set reasonable limits on how large numbers can be, so that invalid identifiers or timestamps are caught. By clearly defining these expectations and checking parsed values against them, your program will handle numbers more reliably. Python code. Parsing integers safely. This material focuses on safely turning messy user text into reliable integers. It explains how to validate input strings before converting them so that only properly formatted numbers are accepted as trusted values. It also shows how to handle bad or unexpected inputs by using try blocks and simple custom validation rules. The goal is to prevent errors and keep your program stable when users provide incorrect or unpredictable numeric input. We begin with a list of raw values that are all written as strings but represent different kinds of numbers. These include whole numbers, a decimal number, a number that uses a comma, a placeholder indicating missing data, a negative value, and a very large value. This diverse set of inputs is used to show how we can safely and effectively convert various user-provided strings into integers. The goal is to demonstrate practical strategies for handling many different numeric formats and potential input problems. We define a helper function called saveParseInt that converts text to an integer in a controlled way. It takes a text input and optional settings for whether negative numbers are allowed and what the maximum value can be. The function first cleans the text by removing spaces and commas so the format is consistent. It then checks for special placeholder values, such as an empty string n/a or none, and returns no result for these. This way, only valid numeric strings are passed on for conversion. The code first checks whether the clean string begins with a plus or minus sign. If it does, that sign is separated from the remaining numeric characters, so the number sign can be handled explicitly. If no sign is present, the code assumes the number is positive and treats the whole string as the numeric part. This ensures the sign is clearly identified and kept separate from the digits for later processing. The code verifies that all remaining characters in the clean string are digits, confirming that it represents a valid number. If it finds any non-digit characters, it returns a special value, such as none, to mark the input as invalid. This check is essential for rejecting strings that cannot be safely converted to integers. The code looks at the first character of the clean string to see if it is a minus sign, which would mean the number is negative. If negative numbers are not allowed, as indicated by a flag set to false, the function immediately returns none. This behavior ensures that when negative values are not permitted, only positive integers are accepted and processed. The code tries to convert a clean string into an integer using base 10 to keep the conversion clear and consistent. If this conversion fails and raises a value error, the code catches the error and returns none instead. This way, invalid input does not crash the program, but is handled safely. Returning none clearly signals that the conversion did not succeed. The code first checks whether a maximum allowed value has been set, and then compares the parsed integer to this limit. If the integer is larger than the maximum, the code returns no result, effectively discarding that value. This behavior keeps all accepted integers within a defined upper boundary. As a result, it adds an extra layer of validation to prevent values that are too large from being used. If all checks succeed, the function returns the integer value, meaning the input string was properly cleaned, validated, and converted within the allowed range. If any check fails at any point, the function returns none instead. This signals that the input was invalid or outside the permitted bounds. The code first prints a header line that labels the output columns. It shows a column for the raw input value, an arrow, and then a column for the parsed integer result. This creates a clear format where each original input is displayed next to the integer value it was converted into. As a result, it is easy to compare the original data with its parsed integer form. We process each raw value in the list by passing it to a helper function that safely converts the text to an integer. In this call, we do not allow negative numbers, and we enforce a maximum value of 1 million, so the result stays within this limit. After each value is parsed, we print both the original text and the resulting integer. This lets us clearly compare the input with the safely validated output. This material explains a script that safely converts a list of raw text inputs into integers. It uses a helper function to clean each string by removing spaces and commas, ignoring special placeholders like n/a, and checking that the remaining characters are numeric. The function also enforces rules, such as rejecting negative numbers and limiting the maximum allowed value. The script then processes each input and prints the original text alongside either the parsed integer or the word none if the input is invalid. This approach helps handle messy user input reliably and avoids common errors in data parsing. Parsing floats and infinity. When working with real numbers in programs, converting text input into floating point values is common, but requires more than just calling a conversion function. You must handle different text formats, white space, and positive or negative signs, and be prepared for inputs that are not valid numbers. Unexpected characters or localized number formats can cause conversion to fail. A good strategy is to validate or clean the input first, and then treat conversion errors as normal situations to handle gracefully, rather than allowing them to crash your program. When parsing floating point numbers, you must account for special values such as positive and negative infinity, and markers that represent undefined numeric results. These values often appear in real data like sensor readings or financial models, and they behave differently from ordinary numbers in calculations and comparisons. Because of this, you need clear rules for whether to accept, transform, or reject them based on your application's requirements. Safe parsing, therefore, means not only converting text to numbers, but also handling these special cases carefully to avoid unexpected behavior. When working with floating point inputs, you must account for rounding, limited precision, and the difference between failed conversions and extreme but valid values. Very large numbers may convert to infinity, which is mathematically correct, but may not be appropriate for contexts like budgets or health data. If converting from a string fails, you can log the error, ask for a corrected value, or fall back to a default. In data processing, infinities can be replaced with special markers, or the affected records can be excluded. Planning for these cases helps keep your floating point data both valid and meaningful for later computations. Python code, parsing floats and infinity. This lesson focuses on safely converting text into floating point numbers, including special values that represent positive or negative infinity. It explains how to detect and handle invalid text that cannot be converted, so that errors do not crash the program, but are managed in a controlled way. You will also see how normal numeric values differ from infinities and from not a number values, which represent undefined or unrepresentable results. Together, these ideas help you build more robust programs that can interpret numeric text inputs correctly and respond gracefully when something goes wrong. We begin with a list of example values that are all written as strings, representing different kinds of numbers. These include a standard decimal number, like 3.14, a negative number with extra spaces, a very large number written in scientific notation, and special floating point values such as positive infinity, negative infinity, and not a number. The list also contains an invalid numeric string, the word 10. This collection is designed to show how Python processes a variety of numeric inputs, including edge cases like infinity, not a number, and values that cannot be converted to numbers at all. We begin by creating an empty list called parsed values that will hold pairs of items. Each pair contains the original text input and either its successfully converted floating point number or an error message if the conversion fails. This structure lets us record both successful and unsuccessful parsing attempts in one place. Keeping this information together makes later processing and analysis of the inputs and their outcomes more straightforward. We process each text entry in the list by trying to convert it into a floating point number. When the conversion works, we record both the original text and the numeric value together. When the conversion fails and raises an error, we catch it and instead record the original text with a note that the conversion failed. This way, we handle both valid and invalid inputs cleanly and keep track of the result for every attempt. The code prints a message to introduce the results of parsing different text inputs into floating point numbers. It prepares the listener to see how these inputs are converted to numeric values. In particular, it draws attention to special floating point behaviors, such as how infinity and not a number values are handled. This sets up a demonstration of both normal and special cases in floating point parsing. The code goes through each original text input and its parsed result stored in a list. For every pair, it prints a message that shows the original string alongside the value it was parsed into. This makes it easy to see how each input was interpreted. You can quickly tell whether a string was successfully converted to a floating point number or if the conversion failed. We begin by setting a variable that will hold the finite sum equal to 0. This variable will store the running total of all parsed values that are valid floating point numbers. By initializing it to 0, any later additions will correctly build up the sum of numbers that are neither infinite nor not a number. We go through each parsed value and focus on the numeric part, checking that it is a valid floating point number. We exclude any values that are positive or negative infinity, and we also filter out nan values by confirming that the number equals itself. Only when these checks pass do we add the value to the running total. This way, the final sum includes only finite, valid numbers and ignores all invalid or infinite entries. The code calculates and prints the sum of all valid numeric values parsed from a list of text inputs. It does this by iterating through the parsed values and keeping only those that are floating point numbers and not equal to positive or negative infinity. It also excludes any value that is not a number by checking that the value is equal to itself. Since a not a number value fails this test, the remaining finite not a number values are added together, and this total is stored and then printed to the console. This script shows how to safely convert text inputs into floating point numbers in Python, including special values like infinity and not a number. It goes through a list of strings, tries to turn each one into a float, and records whether the conversion worked or failed. The script then prints each original string with its parsed result to illustrate how Python interprets values such as positive infinity, negative infinity, and not a number. Finally, it computes the sum of only the finite valid numbers, excluding infinities and not a number values, to demonstrate careful handling of special floating point cases in calculations. Complex from inputs. In Python, complex numbers represent values with both real and imaginary parts, which is especially useful in areas like signal processing and electrical engineering. You can picture a complex number as a point with a real component on the horizontal axis and an imaginary component on the vertical axis, usually stored as floating point values. This lets you bundle two related quantities, such as magnitude and phase, or value and adjustment, into a single complex value. Python's complex type supports arithmetic and comparisons that respect this two-part structure, making it a powerful way to work with such multidimensional data. In Python, when you create a complex number from an integer or a float, that value becomes the real part, and the imaginary part is set to 0, which makes it easy to extend real calculations into the complex domain. If you provide separate values for the real and imaginary parts, Python converts both to floats, so you can mix different numeric types. You can also build complex numbers from strings, but the text must follow a format that Python recognizes, or the conversion will fail. Because of this, it is important to validate and clean up any text input before using it to create complex numbers. When working with complex numbers in real applications, you need to guard against bad input to avoid errors. Data from sources like sensors or spreadsheets may contain missing values or unexpected text. So you should first clean and validate the real and imaginary parts. Check that each part matches a numeric pattern, convert it to a floating point number, and watch out for very large values or special cases like infinity that can cause problems. By treating this as a two-step process, first securing valid numeric components and then building the complex number, you improve both data quality and code reliability. Python code, complex from inputs. This section focuses on safely constructing complex numbers from reliable numeric inputs. First, it converts string values into trusted floating point numbers for the real and imaginary components. It then uses these validated floats to build the complex number. The process also emphasizes how to safely handle cases where the imaginary part is invalid, missing, or otherwise problematic, so that errors are caught and managed rather than silently accepted. The script starts by importing the math library so its functions are available for numeric checks or calculations later in the code. Even though the snippet shown does not directly use these functions, including the library prepares the program to handle numeric operations more robustly if they are needed. We begin by taking two pieces of text input that represent numbers. One holds the real part of a complex number, written as 3.5, and the other holds the imaginary part, written as -2.0. These values come from external sources and are stored as text rather than as numeric data. Setting them up this way prepares us to convert the text into actual numeric values, so the complex number can be processed further in calculations. The code assigns a variable to a string labeled n/a, which represents a problematic imaginary part taken from a spreadsheet. This string is not a valid number, so it is used as an example of input that can fail when converted to a numeric type. The main purpose is to show how to safely detect and handle such invalid numeric data in later parts of the program. The code first prints the original text value used for the real part of a complex number, allowing you to confirm what was received before any conversion. It then prints the original text value for the imaginary part for the same reason. These outputs act as a simple debugging aid, helping you verify that both inputs were captured correctly from their source. We first convert the text for the real part into a floating point number so we have a usable numeric value. Then do the same for the imaginary part. Using these two float values, we construct a complex number and print it to show the result. If either conversion fails and raises a value error, we catch it and print a message indicating that the main numeric text could not be converted successfully. We try to convert the imaginary part of the input into a floating point number, and if this fails, because the text is not numeric, a value error is raised. We catch this error and respond by announcing that the imaginary text is invalid and that we will use 0 instead. We then set the imaginary part to 0 as a safe default, so later calculations can continue without crashing. The code creates a complex number using a valid real part and a fallback imaginary part. If converting the imaginary input fails, it safely replaces it with 0. This guarantees that a complex number is still constructed even when the imaginary value is invalid. Finally, the program prints the resulting complex number, showing the real part and the fallback imaginary value. This script shows how to safely build complex numbers from text input by first converting the real and imaginary parts from strings to floating point values. If both conversions work, it combines them into a complex number and prints the result. When a conversion fails, such as when the imaginary part is given as an invalid value, like n/a, the script catches the error and uses 0 instead. This prevents the program from crashing and ensures that a valid complex number is still produced even when the input data is unreliable. Truthiness and Boolean logic. Truthiness of values. In Python, conditions do not rely only on the explicit values true and false, but on the idea of truthiness for almost any object. In if statements and while loops, non-zero numbers are usually treated as true, while zero values are treated as false. This behavior lets you write shorter, cleaner conditions without always comparing directly to true or false. However, you must understand which values count as something and which count as nothing in a logical sense, so your conditions behave as you expect. In Python, many data types follow truthiness rules similar to numbers. Empty containers, such as strings, lists, tuples, dictionaries, and sets, are treated as false, while non-empty ones are treated as true. This means you can write conditions that simply check the container itself to see if it has content, instead of comparing its length. As a result, your code becomes simpler and focuses on whether there is data to process or act on. In Python, many built-in types and custom objects have their own rules for when they count as true or false. Most of the time, these objects are treated as true unless they are defined to behave like something empty or unusable. For example, a database connection or network response might be considered false when it is in an error state and true when it is ready to use. When such objects appear in conditions, you can think of it as checking whether they are in a valid, usable state. Understanding this helps you predict how complex expressions behave and design your own data types with intuitive truthiness. Python code, truthiness of values. This material explains how different values behave in Boolean conditions. It shows which numbers and containers are treated as true or false when a program evaluates them. Understanding this helps you predict truthiness when writing if statements and loops. The goal is to make it easier to reason about how your code will run based on the values it checks. We create a list of numeric values, including positive and negative integers, floating point numbers, and complex numbers, to see how they behave in Boolean contexts in Python. The list includes examples like 0 and 1, 0.0 and 2.5, and complex numbers such as 0 plus 0j and 1 plus 0j. By examining these different numeric types, we can observe which specific values Python treats as true and which it treats as false when used in conditions. The code adds several different elements to an existing list in order to explore truthiness in Python. It includes empty and non-empty strings, empty and non-empty lists, empty and non-empty dictionaries, and empty and non-empty sets. By comparing how these empty and filled versions behave in Boolean contexts, the example shows that most empty containers are considered false, while those with content are considered true. We define a class called fakeConnection to simulate a network connection. Its initialization method takes a parameter that indicates whether the connection is active. This value is stored as an instance variable, so each fakeConnection object can keep track of its own connection state independently. This method defines how an object of the class behaves in a true or false test by returning the value of its connected attribute. If connected is true, the object is treated as true. And if connected is false, the object is treated as false. As a result, you can use these objects directly in conditional statements, which makes the code more intuitive and easier to read. This example creates two fakeConnection objects and adds them to a list, one initialized with a false state and the other with a true state. The purpose is to show that custom objects can control how they behave in Boolean contexts. By implementing a special method that returns true or false based on their internal state, these objects define their own truthiness. This allows them to be used naturally in conditions, just like built-in Boolean values. The code first prints a short header that explains what the output will show. It tells the user that each value will be listed along with a description and its Boolean truthiness. This introduction prepares the reader for the loop that follows, where each item in the list is evaluated. The result is a clear, labeled display of each value and whether it is considered true or false in a Boolean context. This code goes through each item in a list and builds a short description that includes the item's type and a readable version of its value. It uses a function to get the class name and another function to get a string representation of the item, then formats this information so it lines up neatly in the output. Next, it checks the item's truthiness using the Boolean function to see whether it is treated as true or false in a logical context. Finally, it prints the description together with the Boolean result, showing how each different item behaves when evaluated as true or false. This script demonstrates how Python decides whether different values count as true or false in a Boolean context. It tests numbers, strings, lists, dictionaries, sets, and a custom object to see how each behaves. In Python, 0 and 0.0 are false, while any non-zero number is true. Empty strings, lists, dictionaries, and sets are false, and non-empty ones are true. The custom class shows that objects can define their own truthiness through a special Boolean method. Running the script prints each value, its type, and whether it evaluates to true or false, illustrating how conditions work for different data types. Short-circuit logic. Short-circuit logic in Python evaluates logical expressions from left to right and may stop early once the result is known. For an AND operation, if the first part is false, Python immediately returns that value without checking the rest. For an OR operation, if the first part is true, it returns that value right away. This means the final result can be one of the original values, not just a simple true or false, based on Python's rules for short-circuit evaluation and truthiness. Short-circuit logic means that an expression may stop being evaluated as soon as the final result is known. This is useful because it can skip unnecessary work, such as checking an attribute only if an object is not null, or avoiding an expensive database query when a simpler test already fails. However, it can also cause bugs if you expect every part of a condition to run. For example, when relying on a function call to update state or record a log. Understanding that evaluation can stop early helps you know which parts of your code actually execute and which may be skipped. In Python, short-circuit logic works together with truthiness rules and the fact that logical operators return one of their original operands, not just true or false. As a result, when you use these operators to set default values or pick non-empty inputs, the outcome is often one of the original values rather than a simple Boolean. This behavior depends on whether each value is considered true or false, and in numeric cases, 0 counts as false, which can cause surprises when mixed with other types. By understanding which expressions are skipped and which values are returned during short-circuit evaluation, you can better predict your code's behavior and avoid unintended type or value conversions. Python code. Short-circuit logic. Short-circuit logic means that logical operations can stop early, as soon as the result is known. With an AND condition, evaluation stops as soon as one part is false, because the whole condition cannot be true. With an OR condition, evaluation stops as soon as one part is true, because that is enough to make the whole condition true. This behavior allows you to write simple, safe checks that avoid unnecessary or unsafe evaluations once the outcome is determined. The code starts by creating two variables to hold user input, one for a name and one for an age. The name variable is set to an empty value as a placeholder when no name is given. The age variable is set to 0 as a default when no valid number is entered. These starting values help the program handle missing or invalid input without causing errors, so it can continue running safely. This example demonstrates short-circuit logic with the logical AND operator. We check whether a username is not empty and whether its length is greater than 3. Because of short-circuit behavior, if the username is empty, the second condition is not evaluated, and the overall result is automatically false. Finally, we display the result of this check to show whether both conditions were satisfied. This example demonstrates short-circuit logic using the OR operator. We set up a fallback name called default name with the value guessed user. Then we evaluate an expression that first checks whether the username value is considered true. If username is an empty string, which counts as false, the expression skips it and instead uses the default name. Finally, we print the result to show whether the username or the fallback default name was selected. This example introduces short-circuit logic using a division scenario. The program announces that it is demonstrating short-circuit behavior, then sets a variable to 0. Since dividing by 0 would cause an error, this setup is used to show that short-circuit logic can prevent the division from happening. The key idea is that the division is only attempted if the value is not 0, avoiding a division by 0 error. We first check that the number is not 0, so we avoid a division by 0 error. Only if this check passes do we then test whether 10 divided by that number is greater than 1. This uses short-circuit logic with a logical AND, so if the first condition fails, the division is never attempted. Finally, we print whether this safe division condition was satisfied. The code first prints a message explaining that it will demonstrate short-circuit logic to select the first numeric value that is true. It then sets a backup distance in miles to 5. This backup value serves as a default distance to use if the sensor does not return a valid reading. The program sets the sensor distance to 0, which represents a failed or invalid reading, and then uses a logical OR operation to choose between this value and a backup distance. Because 0 is treated as false, the OR operation skips it and selects the backup value of 5 miles as the first true option. The program then prints this chosen distance, so the output shows the backup distance of 5 miles. This script illustrates how short-circuit logic works with Python's logical operators. With the AND operator, evaluation stops as soon as a condition is false. So checking that a username is non-empty and long enough fails immediately when the username is an empty string. With the OR operator, evaluation stops when a condition is true. So an empty username causes the code to fall back to a default guessed user. The AND operator is also used to prevent division by 0 by first checking that a number is not 0, which stops the division when the number is 0. Finally, the OR operator chooses the first true value between a sensor distance and a backup distance. So when the sensor distance is 0, it uses the backup distance of 5 miles instead. Common truthiness pitfalls. In programming, truthiness can differ from everyday ideas of true and false, so it is important to know how values are actually evaluated. Any non-zero number, whether positive or negative, is treated as true, while 0 is treated as false. Empty containers such as strings or lists are considered false, but any non-empty version is true, no matter what it holds. This behavior can cause bugs when you need to distinguish between having no data and having data you do not want, because even a single 0 or placeholder still counts as true. Understanding these rules is essential when checking configurations, query results, or user input. When you combine Boolean logic with operators that also work on numbers, be careful, because the result may be one of the original values instead of a simple true or false. This behavior can be handy for choosing default values, but it is dangerous if you later assume the result is purely Boolean. You might think you are working with a generic truth value, when in fact, you are holding a specific number that just happens to be treated as true. This can cause confusion when chaining conditions, comparing against thresholds, or debugging, because you are really passing around the original operands, not abstract Boolean values. In Boolean contexts, do not assume that values which look similar will behave the same. A string that contains the word false or the character 0 is still considered true because it is not empty. And a list full of zeros is also true because the list itself is not empty. These differences can cause logic errors, such as treating a user's no as if it were yes. To avoid this, be explicit about how you convert values to Booleans. Check for emptiness separately. And remember that truthiness follows the rules of the data type, not everyday human meanings. Python code, common truthiness pitfalls. This section focuses on common truthiness pitfalls in programming, especially with numbers and containers. It explains that some values, like 0 or empty containers, may be treated as false, while non-zero numbers and non-empty containers are treated as true, which can lead to subtle bugs. It also shows that logical operators often return one of their original operands instead of a simple true or false value. Finally, it highlights that strings and non-empty containers can behave in surprising ways in logical expressions because of these truthiness rules. This example explains how Python treats numbers as true or false values. When the function checks the truth value of 0, it is evaluated as false. In contrast, any non-zero number, including negative numbers, is evaluated as true. The output shows this by giving false for 0 and true for -5, demonstrating Python's truthiness rules for numeric values. This section explains how Python decides whether a list is considered true or false. An empty list is treated as false in a Boolean context. In contrast, a list that contains a value, even if that value is 0, is treated as true. The key idea is that any non-empty container is considered true, regardless of the truthiness of the elements inside it. In this example, the logical OR operator is used to evaluate two numbers. Python treats 0 as false, so OR skips it and moves on to the next value, which is 10. Since 10 is considered true, the expression returns 10 as the result. When we print the value and its type, we see that the result is 10 and that it is an integer. This shows that the OR operator returns the first value that is considered true. This example shows that the logical AND operator in Python returns one of the original values, not just a true or false result. When we evaluate 5 and 100, both numbers are considered true values, so the operator returns the second value, which is 100. That value is stored in a variable, and when we print it, we see that the result is 100, and its type is an integer. In this example, we look at the truthiness of a string that looks like a number. a variable is set to the text value 0, and then its truthiness is checked using the Boolean conversion function. Even though it seems like numeric 0, the value is treated as true because any non-empty string in Python is considered truthy. The program then prints the result of this truthiness check along with the original string, showing that the string 0 is indeed truthy and keeps its original content. This example shows that in Python, a list is considered true as long as it is not empty, even if all its elements are 0. We create a list of 3 zeros and then use the built-in truthiness check to evaluate it. Because the list contains items, it evaluates to true, despite the values being 0. The program then prints this truth value along with the list to confirm that the non-empty list is treated as true, and to display its contents. This script explains how Python decides whether values are treated as true or false, which can sometimes be surprising. It shows that 0 counts as false, but any non-zero number, even a -1, is true. An empty list is false, while any non-empty list, including one that holds only zeros, is true. It also demonstrates that logical operators like OR and AND return one of their original values instead of a simple true or false, and that a string containing the character 0 is still considered true. Overall, the examples highlight that Python's idea of truthiness depends on the type and content of a value, not just on obvious true or false labels. Safe numeric aggregation. Safe sum start value. When aggregating numbers, you should always start with a clear initial value, usually 0, to keep calculations accurate and predictable. Using a non-neutral starting value, such as 1, can distort the final result. The initial value also determines the data type of the total. So beginning with an integer 0 keeps the sum as an integer, while starting with a floating point 0 produces a floating point result. This is especially important when combining values from lists or databases, where you want to avoid unexpected type changes or loss of precision, particularly in financial or scientific data. When working with operations that combine values, it is important to choose a safe starting value, especially when the data might be empty after filtering. If your logic assumes at least one item, you can run into errors when there are none. Using a starting value that acts as the identity for addition, such as 0, avoids this problem. It gives you a predictable result, like a total of 0 instead of an error, which keeps later calculations, such as averages or reports, consistent and reliable. When choosing a starting value for an aggregation, it is important to match both the numeric type and the meaning of the data. If you are summing durations stored as floating point numbers, start with a floating point 0. In signal processing, use a complex 0 to keep both real and imaginary parts. And in financial calculations, use a decimal 0 to reduce rounding errors. In all cases, the initial value should be a neutral element that fits the data type, so the aggregation behaves predictably, even when there are no elements to combine. Python code safe sum start value. This section focuses on choosing safe starting values when adding numbers and on how those choices affect the result. It explains how different numeric types, such as integers, floating point numbers, and decimal values, behave when used as the starting point for a sum. It also shows what happens when you sum an empty collection with a given start value, and how that determines the final total. Finally, it compares the totals you get for simple expense data when using integers, floats, and decimals, so you can see the differences between these numeric types in practice. We use the decimal module, specifically the decimal type and the getContext function, to perform precise decimal arithmetic. Decimal is important for tasks like financial calculations, where small rounding errors from regular floating point numbers can cause problems. The getContext function lets us control settings such as the precision used in these decimal operations. By setting the precision, we ensure that our calculations are accurate to the required number of decimal places. This code uses the decimal library's context settings to set the precision of decimal arithmetic to 10 digits. By doing this, all later decimal calculations are carried out with up to 10 significant figures. This control over precision helps maintain consistent accuracy. It is especially important in financial calculations, where even small rounding errors can matter. We define a list of monthly expenses in dollars, containing 3 integer values, 19, 35, and 46. These numbers represent the total expenses for each month. This simple list will later be used to show how the sum function works when it adds together integer values. We create a list of expenses using floating point numbers, which are numbers that include decimal values. These expenses are measured in dollars and can include amounts like 19.75, 35.50, or 46.25. Using floating point numbers is important because it lets us represent currency with the precision needed for accurate financial calculations. This line calculates and prints the total of a list of monthly expenses stored as integers. It uses the sum function without a starting value, so the function automatically starts from 0. As a result, it simply adds all the numbers in the list and returns the overall total. The mention of a non-empty list just means there is at least one expense value to add. This example shows what happens when you use the sum function on an empty list while giving it a starting value of 0. Because there are no elements to add, the function simply returns the start value. Setting the start to 0 makes the result 0, which matches what we expect when nothing is being added. This is helpful for keeping calculations consistent when you might be working with datasets that could be empty. This line calculates and prints the total of a list of expenses stored as floating point numbers in dollars. It uses the sum function with a starting value of 0.0, so the calculation begins as a float. This helps keep the result in floating point form and avoids type issues. The final output is the total expenses represented as a floating point number. We create a list of 3 high-precision decimal values representing money: 19.75, 35.50, and 46.25. Each value is stored as a decimal object rather than a regular floating point number. Using decimal for currency helps maintain accurate calculations and avoids rounding errors that can occur with standard floating point arithmetic. This line calculates and prints the total of a list of expenses, where each expense is stored as a decimal value. It uses the sum function with a starting value of decimal 0, so that all additions stay in the decimal type. This ensures precise results, which is especially important for financial calculations where accuracy matters. This line shows what happens when you sum an empty list using the decimal library, with the starting value set to decimal 0. It demonstrates that when the iterable is empty, the sum function simply returns the start value. Because the start value is a decimal, the result is also a decimal. This keeps the numeric type consistent, even when there are no elements to add. This example prints a message to show what happens when you give the sum function a non-zero starting value. It adds up a list of monthly expenses, which are integers, but begins the total at 1 instead of the default 0. As a result, the final total is always 1 higher than the actual sum of the expenses. This demonstrates that choosing an inappropriate start value can introduce a bias and lead to unintended results. This script shows how the sum function behaves with different numeric types and starting values. It first sums a list of integers using the default start, then uses an explicit 0 start with an empty list to confirm the result is 0. For floating point numbers, it uses a floating 0 start to keep precision. And for decimal numbers, it sets a high precision context and starts from a decimal 0 to maintain accuracy. It also demonstrates that summing an empty list with a decimal start still returns 0. Finally, it warns that using a non-zero start value will shift the result by that amount. So choosing the start value carefully is important. Custom ordering with key. When you aggregate numeric data to find a minimum or maximum, you can use a key function to decide what counts as the smallest or largest value. This function transforms each item before comparison, so you can order data based on a specific criterion. For example, with city data that includes population and income, the key function can pull out the income value, and the aggregation will then select the city with the highest income. This approach lets you work with complex data structures while focusing on one important numeric attribute. Using a key function for custom ordering is useful when the number you care about is not stored directly, but must be computed. For example, when comparing investment portfolios, you can define a key function that calculates a composite score, such as average return divided by volatility, and adjusted for fees to rank them by risk-adjusted performance. In sports analytics, you can similarly rank players by contribution per minute instead of total points by using a key function that computes points per minute, or an efficiency index. In both cases, the key function lets your aggregation focus on derived metrics that match your specific analytical goals. When using custom ordering based on a key function, you must plan for missing or bad data. If some items lack the needed attributes or the key function fails, the sort can break or give unreliable results. To avoid this, make sure the key function always returns a valid numeric score. For example, by assigning default values or skipping incomplete entries. This is especially important in real tasks like ranking accounts by balance or comparing energy efficiency, where missing data is common. By carefully designing and checking your key function, you keep control over the ordering and ensure it still reflects your criteria even when the data is imperfect. Python code. Custom ordering with key. This lesson shows how to use key functions with the minimum and maximum operations to control how items are ordered. Instead of picking cities by their largest population, you can choose them by their highest income values. It also explains how to safely handle missing income data by assigning a default numeric score, so the selection process remains robust, even when some values are not available. We define a list of cities where each city is represented as a dictionary with a name, population, and income. The cities are Springfield, Shelbyville, Ogdenville, and North Haverbrook, each with a specified population, while Ogdenville's income is left unspecified and set to none. Organizing the data this way lets us easily compare cities and perform operations later, such as finding which city has the highest income or the largest population. We define an income score function that takes a city dictionary and extracts its income value. If the income is missing, the function uses 0 as a default, so that cities without income data are treated as having the lowest income. It then converts the income to a floating point number to keep comparisons consistent. This provides a reliable numeric score for each city, making it safe to compare cities based on income, even when some values are missing. To find the city with the highest income, we use a maximum function together with a custom key function that focuses on income. This key function, called the income score, tells the maximum function which value in each city record to compare. It also safely handles missing income values by treating them as 0. As a result, the method reliably identifies the richest city based on income rather than other attributes like population. To find the city with the largest population, we use a maximum function together with a key function. The key function is defined using a short lambda expression that takes a city dictionary and returns its population value. This tells the maximum function to compare cities based on population rather than any other attribute. As a result, it selects the city with the highest population, showing how a key function can control which attribute drives the comparison. We first identify and print the city with the highest income by using a custom key function that evaluates each city's income score. And we also show that score to make clear what value was compared. Then we find and print the city with the largest population by directly comparing their population values. This example shows that by changing the key function, we can change the criterion used to select the maximum, allowing us to focus on different attributes such as income instead of population. This material explains how custom key functions can change the way Python's minimum and maximum functions select data. Using a list of cities with population and income values, the goal is to find the richest city and the most populated city. A helper function returns a city's income when it exists, or 0 when it is missing, so cities without income data are treated as having the lowest income. With this custom key, the script identifies Shelbyville as having the highest income, while using population directly identifies Springfield as the most populated. This shows how choosing different key functions lets you flexibly analyze data based on different attributes. Handling empty iterables. When using Python to aggregate numbers over an iterable, you must consider what happens if the iterable is empty. This can occur in real situations, such as when a database query returns no rows or a sensor provides no readings. Calling an aggregation function on empty data without checking first can cause runtime errors or misleading results. Some functions require a starting value for empty inputs, while others will raise an exception. By handling these cases deliberately, you keep your code robust and predictable, even when data is missing. When working with empty iterables in Python, you must decide in advance what result is appropriate for your situation. For example, if you are summing daily sales and there are no transactions, returning 0 makes sense because it means no sales occurred. But for operations like finding a minimum or maximum sale price, returning a numeric value when there are no sales can be misleading. In those cases, you should detect the empty iterable and either skip the calculation, use a special marker, or raise an error to be handled elsewhere. Whatever you choose, make sure this behavior is intentional and clearly documented so others understand how empty results are treated. As your programs grow more complex, it becomes important to handle empty groups of data during aggregation. For example, if you filter out invalid sensor readings and then group temperatures by hour, some hours may end up with no valid readings. Aggregating over these empty groups can cause errors or misleading results. To avoid this, always check whether a group is empty before computing summaries, or define sensible default values. This practice helps ensure that your numeric results remain accurate and reliable in data analysis tasks. Python code: handling empty iterables. This section explains how to safely handle empty data when using functions that add values or find minimums and maximums. It shows that when a list of sales has values, these functions work as expected. But when the list is empty, they can cause errors. To prevent this, you can provide default values so the functions still return a sensible result even when no data is present. The goal is to clearly compare what happens with non-empty and empty sales lists and highlight how default values keep your code from failing. We create a list to store sales figures in dollars for a busy day at the store, where each value is a floating point number representing a single transaction. Putting these amounts into one list makes it easy to work with the data. For example, we can quickly calculate the total sales for the day or find the smallest and largest transaction amounts. This approach helps us organize and analyze the sales data efficiently. We create an empty list to represent a day when the store was closed and no sales were recorded. This empty list stands in for missing sales data on that day. By initializing it this way, we can safely pass it into calculations or functions that expect a list. As a result, operations such as finding the total, minimum, or maximum can be handled without causing errors due to the lack of data. To find the total sales for a busy day, we apply the sum function to the list of sales for that day. We set the starting value to 0.0 so that, if the list is empty, the result is still a numeric 0. This avoids errors and always produces a valid numeric result, even when there are no sales to add. To find the total sales for a day when the store was closed, we apply the sum function to the list of sales for that day. Because the list is empty, we give the function a starting value of 0, so it returns a numeric result. This avoids errors and guarantees that even with no sales data, the total is correctly reported as 0. The describe day sales function takes a list of sales and a label for the day, and first checks whether the sales list is empty. If there are no sales, it reports that no sales data was recorded for that day and then stops. This early check avoids errors that would happen if the function tried to find a minimum or maximum value in an empty list. To summarize the day's sales, we first use a minimum function to find the lowest sales value in the list, then a maximum function to find the highest value. We then compute the total sales by adding all the values together, starting from 0, so the result is valid even if the list has no entries. Finally, we output the day's label along with these minimum, maximum, and total figures to give a clear overview of that day's sales performance. This line displays the total sales in dollars for a busy day by using a variable that stores the sum of all sales from that day. By labeling the output as the busy day total sales in dollars, it clearly explains what the number represents. This helps users immediately understand the context and meaning of the result they see. This code prints a message showing the total sales in dollars for a day when the store was closed. It uses a value that comes from adding up an empty list of sales starting from 0. As a result, even if there are no sales, the total is reported as the numeric value 0. This avoids errors and clearly indicates that there was no sales activity that day. The describe day sales function is called with a list of busy day sales and the label busy store day. It first checks whether the sales list is empty, and since it has data, it continues. The function then finds the minimum sale, the maximum sale, and the total sales using built-in operations. Finally, it prints the label busy store day along with these 3 values to give a concise summary of the day's sales performance. The describe day sales function is called with the closed day sales data and the label closed store day. It first checks whether the sales list is empty. Because the closed day sales list has no entries, the function reports that no sales data was recorded for that day. This check is important because it avoids errors that would occur if you tried to use operations like finding the minimum or maximum on an empty list. This script shows how to safely handle empty lists when working with sales data in Python. It calculates total sales for a busy day using the built-in sum function, and for a closed day, it uses sum with a starting value of 0, so the result is 0 instead of causing problems. The script also defines a helper function that first checks whether the sales list is empty before computing the minimum, maximum, and total values. This avoids errors that occur when calling minimum or maximum on an empty list and allows the program to clearly report that there is no sales data for the closed day. In this lecture, you learned to use int, float, complex, and bool to construct scalar values from various input types safely. Predict how Python 3.12 evaluates truthiness and numeric conversions in common expressions. And apply sum, min, and max to numeric iterables while handling edge cases such as empty inputs. In the next lecture, Lecture B, we will go over strings and bytes.
Thank you for your attention. See you all in the next lecture.